So in an AC system, in an AC system, I've got this alternating current that goes up through here and gets the zero mark is at 180 degrees and 270 degrees, 360 degrees for one full rotation, electrical rotation, one full cycle, two alternations, one positive alternation, one negative alternation. So what is the gate seeing during this alternation? So, let's take a look. So the gate is seeing, let's say the gate is seeing, I go to 90 degrees here. So the gate is seeing, 100 degrees. What am I doing? 180. Okay, so now perhaps the gate is seeing, I've got that resistance. That didn't work. I've got that resistance down fairly low. So I've got a good value because it's a potentiometer, right? So I've got that resistance down fairly low on that pot. I'm not really dialing up the resistance. So if the resistance is low to the pot, then to the gate, then I'm going to have a fair amount of current flowing through there. Okay, so I've got gate current on the positive cycle, and in your lab, you're going to have a diode to be able to stop that current going to the gate like this here, right? Because normally you would have gate current like that going to the gate, but we're going to put a diode in there. So this is what we did here. I know that's super light. Buzzer. Okay, these ones. That gate, it really isn't seeing that. That gate is seeing just nothing because that diode is blocking it. And then it isn't until it gets to this point here again that gate, all of a sudden that current's going to start, pulsing in the positive direction again. Now, what am I going to get for an output? Well, we have to recognize that these devices are not 100% efficient. A diode, a standard forward rectifying diode, takes somewhere around 0.7 volts for it to start to conduct, right? When we start doing bridge rectifiers, we have to deduct that value off of our total output, right? We know that. So we sort of think, well, that's the threshold of the amount of voltage there and the amount of current that I have to be able to apply into the gate, right? Because it is a diode. It's just a PNPN diode in order to get it to conduct. And these ones are somewhere, depending on which one you have, will have a different threshold. Some are 0.1 and some are 0.5 of a volt. So either way, it's still less than a standard rectifying diode. So this threshold, we don't really think of this as a threshold. It is, however, the minimum current level. And the minimum current level, because for the gate, is necessary, because if our minimum current is not if it's not enough, then the gate's not going to turn on. So let's say that whatever this number is, 0.5, 0.1, whatever that is, let's just note that this point right here, where my arrow is that minimum gate current, okay? And let's say we've exceeded that gate current. We have more gate current, so we don't have to worry about it. So we're going to get conduction, and we're going to get conduction only in the positive pulse, right? We're going to get conduction in that positive pulse, and then it's going to try to go negative, but we're not going to allow it in that first component. We're not going to allow it. You're going to actually do a full wave rectified as well using your own bridge rectifier that you're going to make. So we're not going to see any of this conduction through here. We're not going to get any of that through there. And then it, by the time it gets to back into positive territory, we're going to see it start to conduct again, right? So the gate current, what we're seeing at the gate, what we're getting conducting. However, if we look at where this is the minimum value of gate current here, we can see something's happening here. Well, let me zoom in on that. So if you look here, well, look that during this portion, if the gate current doesn't actually, if it doesn't start till here, this is where it's got to get to, is there, it kind of means that this isn't turning on until it gets to there. That is way too wide. So it means it's not turning on until it gets to there. That point right there where my crosshairs are. The current is too low to turn that gate on. We need a certain amount of gate current, right? So that current is not enough to fire the SCR. So it must mean that we're not getting any conduction at that point right over here. We're not, so we wouldn't be getting any of this conduction. That would be gone. Wouldn't see any conduction there. So in which case this line would start right here. That line would start right there, and let's put that in there. So that line would start right there. It would start to conduct at that point. Because we can see over here that the current for the gate wasn't high enough, so it's not going to conduct. Once it gets to high enough, boom, it starts conducting. So let's say that's 22.5, maybe that's somewhere around 18 degrees. If this is 90, that's 45, halfway would be 22.5. Let's say that's 18 degrees, just for something to write down there, right? I mean, whatever it is, it's somewhere around there. Okay. Somewhere around there. So then it stands to reason that if I decrease my gate current, so let's go back here and let's take a look. If I'll use orange here. So here's my gate current. I'm going to apply a gate current here, and I'm just going to thin that out. So I'm going to apply my gate current here. Let's say I go a little bit less. Let's say I go to here. Let's say whatever that value is, okay, it's higher than the minimum gate current. So when I get to here, look, if we look here, right where my crosshairs are there, I've got an arrow out. So right at that arrow there, you can see that, well, I've only just got to the minimum amount of gate current. Well, if I've only just got to that minimum amount of gate current, then it means that it's not actually going to conduct until it gets to there, in which case this conduction would start right there. In other words, you wouldn't see any of this.